During a golf game, both Kylie and Cassandra hit their initial balls out of a sand trap. The height of the golf ball can be modeled by the two equations, where K of x and C of x are the heights of the ball, and x is the time in seconds since the ball was hit. So for those of you that are not as familiar with with golf, let me draw a little picture. Know that I'm not an artist. There's a sand trap. Here's the green at the top. And so here's the player, and they're trying to hit the ball, which is right here, out of the sand trap and up to this point. This is our goal, okay, what we're going to. So if you think of it, it's below this level, so we know that it is below, and they're trying to go up to this point, okay? So if we look at the angle of the ball here in terms of height above ground over time, it's looking like this. We have a parabola that's upside down. It can be accounted for right here. So both players, it says, are in the sand trap again, and they're hitting their balls up on top of the green. And this is the trajectory of the ball in terms of height above the ground and seconds since the ball has been in the air. The first question is, who shot when higher? Now, how I would originally go over this would be with a calculator. Now we get to use DESMOS. So I'm going to plug these two equations into DESMOS, and then I will identify which one represents each color. So I just literally, if you're wondering how did I get to this, I just type in desmos.com. And I'm going to start by plugging in the first one. Y equals negative 14x. Now to find the square, you click down below and you'll see this little square key. Plus 24x minus 4. Okay, so at this time, blue is represented by K for Kylie. I press enter and go to the next one. And actually, just to save myself time, I'm going to copy and paste this in and then make little adjustments. So for Cassandra, it's negative 16x squared plus 22x minus 5.5. Okay, so again, my blue represents, my first equation is Kylie, my green is Cassandra. And now I'm going to take my fingers on the screen and I'm going to lightly move them here just so I have a little bit better view. I'm going to flip back here, and again, my blue is the first equation. So blue is the first equation, and I want to make sure that I don't forget that. So I come over here and I'm going to write, this is my blue equation, and this one is green. So who shot when higher? And I'm able to tell that by just visualizing when I look back to the graph. So I go back to DESMOS, and I can see that, again, this is the height above the ground. Y is the height above the ground of the ball, and your X represents the time the ball is in the air. Okay, so blue goes the highest, and who represents blue? We know that Kylie does. So I can come back to my sheet, and I was able to see that by literally just looking at DESMOS. Now, whose shot hit the ground fastest? So whose shot hits the ground? So this is the ground, and I can see that green, which represents Cassandra, if I click there, it says, okay, it only took 1.07 seconds before Cassandra's ball hits the ground. But for Kylie, it takes 1.527 seconds. And that makes sense. Kylie's ball went higher in the air, so it takes a little bit longer for it to come back down. Again, part B was whose shot hits the ground quickest, and that is going to be Cassandra. The next one says, what is the average rate of change of Kylie's ball from 0 to 0.5? I want you to go back and see this because this is often a problem that students struggle with. So average rate of change over this interval, these are both X values. So 0 and 0.5. I want to know what is the corresponding Y values because these are both represent X values. So if I come to my graph, I'm able to do a couple things. One is I'm able to come here down below, and remember in this particular one they're asking about Kylie. We know that Kylie happens to be the blue, so keep that in mind, okay? So I come to the third graph, and wherever I see an X, I can plug in 0. 1 second. Wherever I see an X, I get to plug in 0. And it gives me the output. My input was 0, my output is -4. My input is 0, my output is -4. I come back here. That means my input is 0, my output is -4. And again, this makes sense because the y-intercept is -4. Now I'm going to put in an input of 0.5 and let's see what the output would be. So I'm coming back here. Again, I copied and pasted Kylie's. How did I know it was Kylie's? Kylie's was the first one. Now I put in 0.5 and I have an output of 4.5, an output of 4.5. So what am I going to do with this? Remember, average rate of change. What that specifically says is that on this graph, from 0 to 0.5, so let's talk about this before we actually do it. From 0 to 0.5, if I can take this back away. Give me a second. Okay, so here's 0, and here's 1, and here's 2. So from 0 to 0.5, that's from this first one to this first really light unit you see here, because you're going by 0.5 units. We want to know on the blue graph that represents Kylie, what's happening? Well, I know it's going up from 0 to 0.5, but how fast is it going up is really the question. How fast is it going up over that particular point from 0 seconds to 0.5 seconds? That's what we're trying to achieve, and really that is part D. Explain what this means. So let's get the answer. Now I'm going to not do mental math. I'm going to come over here, and I remember that average rate of change really is like slope. It's y2 minus y1 over x2 minus x1. It's y2 minus y1 over x2 minus x1. Where am I achieving those numbers? First and second. So I'm typing in 4.5 and a -4, a 0.5 and a 0. Then I'm going to come back, and could I do this by hand? Sure, but I'm going to let the calculator do it for me. So on front I have 4.5 subtract a -4 divided by, notice I am using parentheses, excuse me, divided by a 0.5 subtract 0, and it does the work for you. Again, this is y sub 2 subtract y sub 1 divided by x sub 2 subtract x sub 1. So I got an answer of 17. So 17 feet per second. 17 feet per second. More importantly for part 2 is, what does this mean? It means from 0 seconds to 0.5 seconds, Kylie's golf ball rose at on an average of 17 feet per second. And you'd want to put that out as a complete statement. I just put down the basics there. Again, from 0 to 0.5 seconds, Kylie's ball, we're talking about Kylie's ball, increased on average 17 feet per second. At what moments or moments is Kylie's ball exactly 4 feet above the ground? And it says to round to the nearest hundredth if we have to. Okay, so remember when we look at this graph, 4 feet is right here. And I can see at 2 places is 4 feet. So I'm able to click here. And if it's not exact, I'm going to tell you what we can do. We can come down here, and I can type y equals 4, and there will be a line. And now I want to go right over where they cross. And I click on it. There it is. So when the ball is exactly 4 feet above the ground and the ball is going up, it hasn't hit its maximum yet, they want to know at what point does it hit 4 feet above the ground. Well, one answer before I do any rounding is 0.453 seconds. So the ball goes up, it hits its maximum, it's coming back down, and I can see, oh, okay, at 1.261 seconds, it also is 4 feet above the ground. It's at 2 times. Let's just make this up and say, what if they said at 2 seconds? Well, at 2 seconds, when is the ball 2 seconds above the ground for Kylie? We could do the same thing. I changed the y equals for this horizontal line, and I could see that at 0.304 and at 1.46. I'm just giving you another example here. That's not part of the problem. So I come back here, and I'm going to read carefully. I'm going to read it twice to myself. It says at what moment or moments, and then it specifically says round to the hundredth. Remember, this is tenths, hundredths. So I'm going to look at the 5 and I look behind it. Okay, it's not 5 or above, so approximately 0.45 seconds. Okay, look here and look behind. Oh, I'm not going to round up. Approximately 1.26 seconds. Please remember, be precise with what it asks you to round with.